Hi everybody! I have recorded another video tutorial about shaders in Godot. This time, we will demonstrate how to create a spectrum analyzer that responds to music played by the Godot audio system. This is a nice effect known from various music applications and can be useful for enhancing your game. Let's do it. So, very briefly, a spectrum analyzer checks and displays how strong different signals are at different frequencies. It's like a tool that tells us the power of signals we know and signals we don't know. Usually, it works with electric signals, but it can also check other types like sound or light with the right equipment. To obtain real-time data, our analyzer will use the fast Fourier transform algorithm. There are several ways to calculate something like this, but luckily, we don't have to deal with any of them because Godot will do the computation for us. Let's demonstrate it right away. So, as usual, we'll create a new 2D scene and add a color rect to it as its child node. Let's right-click Scenes, create new scene and call it Analyzer. Okay, and right-click Add Child Node Color Rect. Good. This time we'll set the dimensions to a rectangle, although our shader would also work with a square, of course. So let's do it right here and transform. Let's try it, for example, as 600 by 400. Very well, and we'll add a new shader material to the material property. Shader material, click new shader, canvas item, analyzer GD shader, and we'll put it to the shader folder right here. Create and click to open it. Alright, but now we'll disrupt our usual workflow and instead of writing a shader code first, we'll do some preparatory work. We'll need a data source from the fast Fourier transformation, which we can obtain easily. Let's switch to Audio tab, and here's the master bus, which is always there by default, and we'll add a new effect called the Spectrum Analyzer. There it is. As the next step, we will need to use the data from this channel in the script. Since we've managed with just one channel, all the sounds our application produces will be processed this way. If we wanted to limit the effect to a specific stream, we could allocate a separate channel by clicking Add Bus and route audio through it. I've described this process in the audio section of the Space Shooter tutorial, so if working with audio in Godot is new to you, I definitely recommend checking out that video. The link should be in the description. However, for today's shader, we'll stick with the master channel. Alright, let's get into the script. This time I didn't have to come up with anything from scratch because a guide on using the Spectrum Analyzer effect can be found on GitHub in the Godot demo projects, which belongs to the official Godot engine account. The script will look like this. Let's add a new script to the analyzer. Scene, create, and let's do it right here. So we need to start with some constants. View count. This is basically number of bands. VU stands for volume unit, and it is a number of columns we will see in our spectrum analyzer. Next one is called frag count. Frag max, and it's 11050.0. This is basically the top frequency the analyzer will work with. And finally, const min dB, which we'll set to 60 because there should be some minimal volume to be displayed in the analyzer. Otherwise, there will be a lot of zeros and it would look nice. Okay, and we will of course need to access to the color rect because we need its material to send the shader parameters to. So by clicking the control key and releasing, we generated the already declaration. Very well, and we need the access to the spectrum analyzer, which we define in the ready function. Let's do it now. So spectrum is, and we can obtain it from audio server as a bus effect instance. Get bus effect instance. We have only one bus there, so the index is 0, and we have only one effect, so the effect index is 0 as well. Easy. Alright, that should be everything for the function. Ready. Let's just get rid of this default comments and process. So now I will simply copy and paste script from the mentioned GitHub project. Let's do it very quickly. This is the array we will finally send to the shader, data of the volume for each frequency range. Let's go through the ranges. For I in range 1, view count +1, hertz is I multiplied by frag max divided by view count. Okay. F is spectrum, get magnitude for frequency. This is the built-in function from the spectrum analyzer effect class, and it will give us exactly what we need in the range from previous frequency to the current one. As we know, the analyzer is discrete, not continuous, so there's not like a continuous graph, only a set of columns. That's why we are working with ranges. And let's call it energy, as it is, I would say, audio energy, and clamp it to the range we will work with, which is from 0 to 1. So we need to start at the minimum dB and add. Now let's convert linear value to the decibel value, which is logarithmic. Length. Okay, 1, 2, 3. Divided by min dB, and the boundaries 0 and 1. That should be correct. Alright, and we have the final value we will add to the data array. Data append energy. Great, let's not forget to update the pref frequency value with the current one for the next iteration. Very well, and once this cycle is over, we need to send the material. So we have this color rect, let's call get material function and set a shader parameter, which we will call frag data, and the value is data. Yeah, we were sending the whole array. This is new in Godot 4. It was not possible in Godot 3 and previous versions, but now we can, and we'll show in the shader code how we would define the uniform parameter to contain an array. So it's time to implement our shader. Let's click back to shader editor, make it a bit bigger, and here we go. We'll start with a constant called view count, just like we defined here in the GD script, and it's ready as well. In fact, the only reason, yes, sure, it should be integer here. The only reason I'm making this integer is that we will define a uniform array which must have some dimension, and the dimension must be an integer constant. This is just required by the shading language, so there is no way to go to do it in another way. And other constant float segment count is 40.0. This will be basically the number of LED lights in the column, so that's why I call it segments. And I created it as a float because we'll be doing a lot of calculations, and it is definitely better with floats. And now finally the uniform parameter, uniform float, and this is the trick, view count frac data, just like we defined here as a parameter. All right, fragment function. Okay, so first we'll need to define the coordinates. Vec2 uv is just a standard uv, but as we know, the 0, 0, 0, 0 coordinate is here at the top left, and we want to display the analyzer from bottom to top, not vice versa. So we need to flip the y coordinate, which would be like this. uv y is 1 and minus uv y. Very well. Now we'll calculate the position of the particular LED. Let's do it this way. Float. First, we need to convert the integer constant to a float variable. Otherwise, we would have to do this conversion in every expression we use it, and that would be just too cumbersome. View count is float view count. Great. And now the position of the particular light, vec2, let's call it pos, would be vec2, and the first coordinate, we need some discrete values because we'll be drawing very small rectangles, so it would be uvx by view count. This is exactly why we needed this conversion. Otherwise it would throw an error. It's not possible to multiply a float by an integer. Just this is how the GLCL language works. And divided by the view count to get the whole value, and similarly for the y coordinate, that would be uv dot y by segment count divided by the segment count. Okay, and we have the position. Now we need the value, so let's call it FFT for fast Fourier transformation, and we'll take it from the array we obtained from the script as a uniform parameter, and we need index, and of course we could use uvx multiplied by view count, but this is a float, so the shading language is not happy about that. We need to convert it to integer. Okay, right here. Is it okay? Yes, it is. Perfect. And we have everything to define the color of this particular light. That would be as a vector 3. Let's call it color. And we want something between green and red, because spectrum analyzer usually shows good low volume in green, shades of green, and red when it reaches the critical value, and there could be some kind of clipping. So this is what we'll do, a mix, which is linear interpolation between, let's start with green, and we'll do it as 2, not 1. As we know, the top value for all colors in this scale is 1. But if we work with only that, the colors would be too dark. So let's have some headroom, and the rest will be obtained by the mix function. So vec3, and now red. So 2, 0, 0. And the value of the mix, it would be driven by the y coordinate, but I did some experiments and it looked like it is not exactly what we want to do, so it turned out to be better with a square root of this value. We'll see after the effect is finished that it gives a much better result. Okay, and now we need a mask, because some lights would be just dark as they are not shining, and the rest should be much brighter. So let's define a float. Mask is, and if the position of the particle light is less than the value of the fast Fourier transformation, let's make it shine, otherwise let's keep it in the dark. Okay, this is the color, this is the mask. We finally need a shape of this LED. Let's define it here by the distance from the UV coordinates of the particular position. So it would be like this: fract UV minus position, and multiplied by vector 2, view count and segment count, because that's the number of the lights we want there. And finally we need to subtract 0.5 to put it to the right position. Okay, and let's create the final color, and we want some kind of boundary around these lights. So this is the best done by smooth step. Smooth step, let's do this kind of boundaries, and we want to work with the absolute value of the distance, which could be sometimes negative. And so this is the x coordinate, and multiplied by another smooth step for the y coordinate with the same boundaries, 35, and absolute value distance point y. Alright, and I think that's all. Let's assign the final color to the color value, which is vec4. And of course we need to incorporate everything we just calculated. So it would be LED multiplied by color multiplied by the mask, and the alpha value is 1 as usual. Let's take a look. Perfect, this is exactly what we want. And let's try running the scene. What's wrong? Of course, it's missing semicolon. No, it's not. Get magnitude for frequency. Non-existent function. I think I have some typo here. Let me find it quickly. Frequency range, of course. Sorry. Okay. Let's try it again. Yeah, it's here. Great. But of course we see that nothing is happening, which makes sense because we forgot to use some music for playback. Let's fix it right away. We will add an audio stream player as a child node and use it on one of my tracks, which I recently recorded for another project as a stream. Let's do it. Right click, add child node, audio stream player, here it is, create, and I think it's here in the music folder. Let's drag it here to the stream. Okay. And of course, to avoid controlling the music through the script, we will set autoplay to on directly. Let's run the scene again and we should see the effect in action. Okay, I think it works. But something is not quite right. As we can see, the LEDs in the analyzer are blinking a lot, which is not pleasant for the eyes. Let's stop it. And that's because the signal for the corresponding frequencies often returns to zero, and the shader reacts to each change immediately. It would be better if it could hold the signal level at the original value for a while, contributing to the smoothness of the entire effect. We'll solve this problem by remembering the ongoing maximum and minimum values for each column in the script, and will ensure smoothness through linear interpolation. Okay, but before I do that, let me put the volume down a little bit. I think that it was too loud in the previous part and nobody understood what I was saying. So basically I was talking about the blinking issue of the LEDs and we need to work it out. We need to fix it somehow. Okay, let's get back to the script and do this. Again, it comes from the GitHub project of the official Godot engine account, and the new version of this demo actually solved that in a very neat way. Let me show you. Another constant, which we'll call animation speed, and we'll need a height scale, because once we implement the change, the meters would just drop too much and we want to display the effect over the whole analyzer rectangle. Okay, and as I said, I have a typo here, right? Spectrum. Okay, and fix it here and here. Alright, we need to remember previous values, so let's create min values is an array and max values is an array as well. And we need to initialize these values here, otherwise Godot would complain about the wrong dimension of the array once we start using indexes. So min values, let's resize to the view count and fill it with zeros. Let's do the same for max values, and max. All right. And let's adjust the process function as well. So this will stand is the same, spectrum, magnitude, round, clamp, and first change is here. We need to multiply that by the height scale, and this will be okay. And now, before we send the values to the shader, we must do this linear interpolation calculations. So for I in range view count, if data I is greater than max values I, let's assign a new max value in the else. We don't have a new max value, but we need to keep the previous one and interpolate. So the max values I would be changed to lerp of max values I and data I, and use the animation speed, which can be adjusted later to just work with the smoothness of the effect if necessary. And of course, if it drops too low, data I is less than 0 or equals, min values should be updated as well. Lerp min values I 0, and again the animation speed. Okay, so this is the first step. And now we need to use these values to calculate the data we will send to the shader. Let's create a new array and call it FFT for fast Fourier transformation, and for I in range view count, let's do this, fill this new array FFT append, of course, and we need to do this interpolation between min value and max value, and again using the animation speed. Okay, I think that's everything except this. We are no longer sending data but at FFT. Okay, let's try it out. I hope the music wouldn't be so loud again. Yeah, I think it's better, and I think it's no longer blinking. It looks just like it's supposed to look. So this time we can say that the effect is doing exactly what we expected from it. Good job! You can experiment with the animation speed and other values to tune the effect as you like. It is also possible to click the spectrum analyzer effect in the audio bus and modify its parameters in the inspector. Let me just quickly show. Audio, click the effect, and here it is. Buffer length, tap back position, FFT size, and that's about it. And that's all for today. Thank you for attention. And if you find a use for this effect in your game, I'd love to hear about it in the comments. Have a great day and see you in the next video.